All right, welcome back. If this slide doesn't look familiar, make sure you go back and watch the previous half of this lecture to talk about these four factors. We need to know about those four factors in order to move on to this next example, where we're going to use them to help us predict a pKa value. So let's get started with this one here. Just to think back to our factors, if we look at that functional group is an alcohol. Quickly answer the video question. It's probably a duplicate, but just for practice, answer the video question to correctly fill in the baseline value of an alcohol's pKa. All right, hopefully you all came up with the value of 15. So 15 is a good starting value, right, to predict for some kind of an alcohol. Now, if we think about the other factors that are here compared to, say, our regular alcohol, so this one is definitely going to be around 15. This one is somewhere near 15, but we're not exactly sure where. If we look, now we have, hopefully these fluorines are kind of raising a little red flag in your mind to say, oh yeah, I remember Grace said that they have strong dipoles that they pull toward themselves that could help stabilize a negative charge, right? So when we remove this acidic hydrogen, it will be more stabilized by withdrawing through induction the electron density away from the oxygen and toward those fluorines. So that is a stabilizing factor of induction. We have that here, so I'm going to put a little check mark. When we're comparing to this reference molecule up above, we have the same element, right? It's a hydrogen attached to an oxygen in both cases. In both cases, it's sp3 hybridized, so no difference there. There is no available resonance for this molecule. So induction is kind of the only factor that's different here. So you don't have to have an exact number for this, but let's go ahead and make a quick prediction. Since 15 is our base value here, for our fluorinated fluorinated alcohol, do we think this is going to be greater than or less than 15? Take a second to make your prediction in the video quiz now. So it's going to be around 15, but having those fluorines able to do induction is going to mean that this is going to be less than 15 pKa. It'll probably go down a couple of units, but it's not going to be a big deal. And again, I'm not going to ask you to get exactly right with pKa values because you don't need to be that precise. You just need to know, okay, if I have my base value, I know it's going to be a little more or a little less acidic than the base value. So let's move on to this next example, another alcohol, right? So we should have that same value, our go-to value of an alcohol. And I'm going to use this as a reference compound. It has very similar shape and overall size, but now we're just getting rid of those pi bonds to see what effect those have on acidity. So sorry, let me just fix this. That looked like an IS instead of a 1,5. So 15 is what I was trying to write there. Again, our base value for alcohols. So if we see what other factors we have here, again, they're both the same type of oxygen, sp3 hybridized. It's the same element, oxygen. I don't see any fluorines or chlorines that would hint at induction happening here. So what is the only difference? It's these pi bonds, right? So when you see pi bonds and it doesn't seem like there's much else of a difference, that's a time to be suspicious. Okay, maybe I should check to see if there's resonance. And in the case of this molecule, which is called phenol, there definitely is resonance. So if we think back to that sort of chemical motif that we have to have in place, we need a single bond followed by a double bond. And so it's true that we have that here, so we can do the exact same thing that we did earlier and resonate. And that's basically going to show us that we can bring these lone pair electrons down here, and then we can move these chemical bonds all the way around this ring. This will come up more later in the semester, so you don't need to worry about it for right now. But I'm just going to draw some resonance arrows to show how this can move all the way around the ring, and to show you that not only do we have resonance, but we have several different resonance forms that will take us over this whole ring, right? So that means it's not just holding a charge on one atom, It's not holding a charge over 2 or 3 atoms, it's all 6 in this ring essentially. So that helps spread the negative charge out a lot that will occur once we take off that proton. So again, our factor for this one is resonance. And I'm going to put several check marks here because we have the ability to resonate to several different positions. Again, more on this to come. So if we had to take our base value guess, 15, and decide, is this going to be greater than or less than 15? Make your prediction now. Again, having that resonance is going to be a stabilizing factor when we look at the conjugate base. So this is going to be less than 15. If this is a good reference value that you want to have in your head, this is a supplemental value that I like to have. But for phenol, for this specific molecule, that proton is 10. So this one makes a fairly big difference of 5 pKa units. Again, this is an optional number. You don't need to have that memorized at all. So let's quickly look at using the factors in this acid-base type of problem for a time when maybe you don't know the pKa's off the top of your head. And we won't estimate any pKa's. You can definitely use them if you want to, but we don't have to be able to see the difference here between these two molecules. So quickly, let's identify our acid and base in this situation so that we can start to move some arrows and predict our products. So this is a little bit weird, right? Because there's no explicit hydrogens drawn out, but what is drawing my attention is this right here, that negative charge and a positive lithium ion. So the lithium we don't really care about, it's just there for balance. But having a negative charge, that can pretty much always be a base. So that is my suspicion, is that it's a carbon with a negative charge. It doesn't like to be that way, so that wants to pick up a proton to become more stable, which means that this other piece must be our acid. So when we're asking ourselves about this acid, we have to say, oh, gee, which one is the most acidic proton? So we have a few different options here. We have these ones on the end. We have these ones here in the middle. And then we have this one over here that's right next to this CO double bond. So I'm going to skip over a lot of the reasoning as to why for now. But when you see a hydrogen attached to a carbon that's doubly bonded to an oxygen, you don't ever pick that one. It seems like it's a good option, but I swear it's not. It's not very acidic. So ignore that one for now. Let's choose between these other two. So they seem pretty similar, right? They're both sp3 hybridized carbon atoms. So what's the difference, right? No induction, no difference in hybridization or atomic identity. Again, looking out for that little clue of having a pi bond nearby. So if we look at this hydrogen here in the middle, we have a single bond, double bond, looking for that same pattern. So this one is going to be able to have a nice resonance if we take it off. On the other hand, if we look at this one on the end, that has a single bond. That can't work. That's not the right arrangement of bonds that we need to resonate. So it can't be this one. It must be that one left in the middle. Okay. Let's practice drawing our arrows to show how the base picks up the proton. These electrons here, drawn a little lone pair, pick up this hydrogen, and then these CH electrons here will fall down to sit on that carbon. And now that'll allow us to predict our products, and they will look something like this. And there we go. So thinking about which one is which as far as applying our labels, the base makes a conjugate acid and the acid makes our conjugate base. Okay, so there we go. We've done the predicting the products part and the drawing the arrows part. And for any other question on a quiz or a homework or an exam, I will absolutely draw out all of the steps that you're required to do. For this one, I just wanted to save some space and not draw in all of the instructions. Now, we want to compare the two bases or the two acids to see which one is more stable or less stable. Again, I'm saying these all in the either or because I want you to choose the method that works the best for you. I'm going to demonstrate the method where we evaluate both of the bases to see which one is more stable. And again, let me know if you prefer to talk through the other side of that coin. I'm more than happy. So we're going to compare, and I'm just going to sort of bring these down. so that we can compare them to one another apart from all these other pieces to just make it a little bit more simple. So we'll bring this one down here, get rid of all this extra nonsense, and I'm going to get rid of the lithium too. It's still there, but for our sake, we'll just make it a little bit more simple and exclude it. Okay, so I'll just rearrange these a little bit here. So what I like to do is pull the bases out, and then I tabulate the factors in order to compare them. So if we think about our first factors, elemental, when we're talking about elemental, we're looking at the charge, the atom where that charge is sitting. So we're looking at this one here and that one there. So if we're comparing those two to one another, they're both carbon. So the element itself is the same. That's a tie. They're both sp3 hybrid. Oh, I'm skipping ahead. So they're both carbon, right? So that means their electronegativity is the same and their size is the same. Next, we evaluate the hybridization. And they're both sp3 hybridized. So that's another tie. See, in this way, we can start to tabulate up the factors and see who's quote unquote winning to be more stable. Then we want to consult some induction. So this one with the fluorines has induction, whereas the other one here on the right-hand side does not have. So that one is kind of winning now with the fluorines because it has the only factor so far that will narrow it down. And then the last part is resonance. Now the one with fluorines has no available resonance, but the one with that pi bond to carbon and oxygen does have the ability to resonate. And I'll draw that in with some arrows quickly here. Is again, single double bond motif. So we can have this come down here like so. That's going to change this pi bond to put it up to a negative charge on that oxygen. So in this case, we have two sort of ties with our factors. So we can just ignore these here because they don't tell us anything new. Now we just have to decide between induction and resonance. So as I alluded to before, one of these is often more of a dominating effect than the other. But the other way to think about it is that resonance is a really direct effect. We can set the negative charge on two different atoms. One of those, it sits here. The other one, it actually goes and sits up on the oxygen. That's direct. That's me throwing a can of iced tea at you up on the balcony. Whereas the induction, you're slowly pulling the iced tea through a big old crazy straw. It's just not as strong. So in this case, resonance is absolutely going to win out here and make this conjugate base, let's grab a blue color here. This conjugate base is going to be the most stable conjugate base. So let's translate that back to what it means about the acid. So when we go to compare the acids here and here, the acid that has resonance available to it here is going to create this nice stable conjugate base, which means that it's more willing to be an acid because it's going to make something that's stable. So that means that this acid is the stronger acid than our other conjugate acid, right? So if we look at this acid over here, that hydrogen is fine there, but there's not really anything that's stabilizing it that much for it to come off, right? We have just a little bit of induction, but it's not a lot. So our stronger acid is going to make the most stable conjugate base. And we want to direct this reaction away from the stronger acid and toward the most stable base. So our arrow choice would be something like this, right? If you wanted to double check some pKa values or some close guess pKa values to make sure this isn't equilibrating, I think that would be a good thing to practice on. But for this one, it's going to just go all the way forward and not look back. Okay, so we covered a lot today as far as the 4 factors and applying them to some of these problems. So that means we've got a lot of stuff to work on. The big takeaway from today, as far as what you should want to feel comfortable with, is understanding what the factors are and how to identify them on different compounds, right? And this also will go back to practicing up with your pKa values and working on some acid base type, predict the direction, predict the equilibrium type of problems. That's going to be a big part of the upcoming exam. So I want to make sure it's really solid. And as I always say, make sure you ask questions if you have any about it. Then if you're feeling good with that, if maybe you had a lot of good acid-base chemistry during your Gen Chem, go ahead and look forward a little bit to the last thing we're going to do before the exam here, and that is nomenclature, or how we name chemicals. There's a little bit of a systematic approach to that, so it may be useful to start looking ahead and reading in your book about that. As always, if you have questions, email me, stop by office hours, or put them in the discussion forum to help you and your student colleagues learn. And other than that, take care, stay safe, and I'll see you in the next lecture.